Perfect. So this is a kind of summary talk on the status of the products we deliver to the Copernicus Marine Service for the Northern Baltic Sea. And there are a few slides also on the Arctic and some of the new products we are developing now. So this, as you know, most of the collaborators, this is an effort, teamwork, and it wouldn't be possible without the help of many others here at TMI. Erica, please, if you would change the slide. Thank you. And if I'm going over time or close to use up the 20 minutes, just interrupt me. The DMI is a production unit for the Copernicus Marine Service, and we deliver to 2 thematic assembly centers, also abbreviated to TACs. The SST TAC, to which we deliver products for the Baltic Sea and North Sea domain, and you can see some of those on the left side of the slide. These products are delivered in 2 modes. We have a near-real-time production chain that produces data daily and delivers them daily as well, both at the level 4, so gap-free, but also on the super-collated level 3, so with gaps because of cloud and bad quality. And we also produce multi-year products, both level 4 and level 3S. And you can see the codes on the left side of the slide. And these products are from 1982 and extended to 2023 now. This is a mistake here. And we are planning regular updates, or they've always been regularly updated, but now at a much higher frequency. And they have been previously based on the version 2.1 of the Icea CCI SST, and now we will this year reprocess these multi-year products with the newest version of the Icea CCI dataset. And on the right-hand side, you can see a similar example for the Arctic products we release. It's a combined sea surface temperature and ice surface temperature product. Delivered both near real-time daily from 2019 onwards, but we also have a multi-year product from 1982 up to 2023 as well, also based on the Icea CCI SST and also on the ASTI sea ice surface temperatures that we have been producing at DMI with the help of Met Norway, and now they are produced through the Copernicus, through C3S, so the Copernicus Climate Change Service. Erica, if you would please change the slide, thank you. This is a very rough overview of, on the bottom left side, the schematic of our production chain. So we use level 2 and level 3 uncollated SSTs for the North Sea, Baltic Sea always, and information on the sea ice concentration, which is very relevant for the northern part of the Baltic Sea basin. And we pre-process those to level 3S data, and then we perform bias correction and adjustment, and then an optimal interpolation to derive the level 4 product. And this is a similar chain both for the near real time and for the multi-year. I have to mention that the North Sea Baltic Sea product is at 0.02 degrees grid, and we also have a diurnal product based on the same grid and the same production chain that is available hourly, and it only started in 2022, so we've had only a couple of years of data, and we are very keen on exploring this product. We haven't done very many things with it. But it would be interesting to use, for example, for an analysis of diurnal variability in the Baltic Sea. Erica, if you would please, yeah. So these are some basic statistics on the validation, and on the left side of the slide, on the top table, there's some pulled out examples of the latest validation, or the most recent validation we've had for the near real-time product, level 4 for the Baltic. And we've been validating that with drifting buoys, which are actually not very much available in the Baltic. They are mostly in the North Sea, and also with some moored buoys. So we are looking at almost zero biases and standard deviations not exceeding 0.5 degrees. And the same is the case for the multi-year product. So this is the table on the bottom left side of the slide. Again, for that we have done a validation for almost the entire period of the multi-year product from 82 to 2021. And again, we are looking at biases at about 0.1 degree and standard deviations of 0.5. On the right-hand side of the slide, you can see some recent validation statistics for a week in March 2024. We are having, it's a bit more challenging to validate the hourly product, also keeping in mind that we don't have very many observations in the Baltic. We are doing this validation both for nighttime and daytime separately, but also for all, the entire day, since the product is available at every hour. And what we are looking is that although the biases are relatively low, we have quite higher standard deviations. And of course, for this specific week in March, we had also quite a few observations. But this product has only been, that has gone through no evolution. So we foresee in the future that we will look into improving the validation statistics of that as well. Erica, if you may, yes. This is just a pulled out example of what the hourly product could be used for. So on the top left side of the slide, there is an example of a composite, so a mean SST from that hourly product for the nighttime, so from midnight to 4 a.m. So representative of, let's say, foundation temperature. And the color scale is from 2 degrees to more or less 14 degrees. It's for June 1st, 2021. The middle figure shows the 4 o'clock hourly field of that same day. And then the right-hand side shows the difference between the 4 o'clock hourly field and the foundation temperature of that same day. And we see differences ranging from -1.5 to 1.5 degrees. And overall, there is a tendency for a warmer SST for the 4 o'clock value. So this is an example of how the product could be used for some kind of diurnal warming analysis, which we know is an issue in the Baltic during summer. Erica, if you would please, thank you. One of the things we recently did as an evolution for the Copernicus Marine Service, and that was last year, was to assess, use a tool to assess the effective spatial resolution of the near-real-time product. And we've used fast Fourier transforms, so spectral analysis. We've seen from colleagues in the GHRSST science team and from presentations from colleagues in Barcelona that there are much better tools to assess this, or potentially better tools to assess this. But this was an initial assessment of how was the product performing in terms of resolving smaller scale features closer to the grid spacing of 0.02 kilometers. And for that, we selected 3 subdomains in our domain of interest, and you can see those on the left-hand side, bottom left-hand side figure. It's the blue, purple, and green square, or D1, D2, and D3. Thank you, Erica. And especially the Baltic Sea is very challenging for extracting a domain big enough to do this. So domain 3, for example, is very small. So what you see on the right-hand side for each panel from left to right represents each of the domains. You can see at the top it says D1, D2, and D3. And essentially, it shows the computed spectra for the domain. And this is for our classic product, which is indicated in the legend as a purple dashed line. You probably don't see it plotted because it's overwritten by the other. We use our traditional level 4 product and an updated version of it. And the 2 spectral lines more or less overlap with each other. And we have also plotted for comparison in the green line the similar spectra calculated from the Ostia near-real-time product that is also available on CMEMS. And that was for the test year of 2021. And this is for each of the domains. So with that, we wanted to assess how much signal can we carry to the smaller scales, so to small, in the order of 2 kilometers. And we can see that our product maintains a signal until more or less scales in the order of the grid spacing. But of course, there is a drop in the spectral power from approximately 20 kilometers down. Then you see that as a drop, a more sudden drop. The two dashed black lines that are on top and bottom in every figure are the theoretical -2 and -5.3 curves for the submesoscale and for the mesoscale and submesoscale. So we see that all assessed products are following the expected decrease of power spectra per wavelength. So this is a good initial assessment. Of course, we would like to look more into maybe using better tools and also how we can improve our effective spatial resolution. Erika, thank you for guiding with the pointer. One other thing we produce and we deliver to Copernicus every year is a set of ocean monitoring indicators. And these include a series of indicators starting from the annual mean sea surface temperature anomaly. And we calculate that based on relative climatology, which we recently changed to follow the World Meteorological Organization standards. So it's the climatology from 1991 to 2020. And here you see the annual mean anomaly for 2023, so for last year. For the North Sea and Baltic Sea. So there is overall an annual mean anomaly exceeding 0.5 degrees, and there's only cooling in the a small area of the northern Atlantic. These are not yet published by the Copernicus Marine Service, but they will be published later in the year. So this is one example of an ocean monitoring indicator. Erika, if you may please change the slide. Another monitoring indicator we produce is a monthly mean anomaly, and we have also recently, also relative to the 1991-2020 climatology, and we have recently changed those to go back to 1982. So there's the full period of the data set available now calculated, and what you see on the left panel is the anomaly for the combined North Sea and Baltic Sea domain. And on the right-hand side, you see that only for the Baltic Sea domain, which is assumed to be anything east of 9 degrees east in longitude. And when we look at the average trend, we see 0.029 degrees Celsius per year for the combined domain and 0.038 degrees Celsius per year for the Baltic Sea, which if you calculate it for the 42 years of the data set is about 1.2 degrees warming for the combined domain and 1.3 or 4 degrees for the Baltic Sea. And on top of the monthly mean anomalies, which are the cyan or green lines, we also compute a 1 year moving mean, which is the blue line. Thank you, Erika. Can we maybe move? Yeah. And the last ocean monitoring indicator we provide is the cumulative trend as the rate of change per year divided by the number of years. And again, we have recently changed that definition to go from 1982 instead of 1993 like it used to be. So it uses the entire data set. And here you see that pretty much in all the domain we have positive and probably above 1 degree cumulative trends for North Sea and Baltic Sea as well. And based on these ocean monitoring indicators, go ahead, Erika. That was good. That was a good transition. We do the same for the Arctic SST product, but before I go to the ocean monitoring indicators, just a quick overview of that. As I mentioned in the beginning, we produce a daily near real-time combined sea surface temperature and ice surface temperature product. and that has been available from 2019 onwards. We have a very good validation of the SST component, and there is an example for the year 2016 to 2017. That was a test year of the validation. The product is available from 2019 onwards, and we were looking at 0.1 degrees of a bias and a standard deviation of 0.55. Validating the ice surface temperature is much more challenging because of the lack of in situ data for the ice surface temperature. So typically we use buoys, and that means 2-meter temperatures, and that means that our validation statistics are much worse. We are looking at biases in the order of minus 2.8 degrees and very high standard deviations in the order of 4 degrees, and that's because we are essentially comparing different things. As I mentioned also in the beginning, there is a multi-year product as well that we have available, and that one has a very nice publication attached to it from our colleague here at Icea. There has been an extensive work on that multi-year product. And as you see from the table on the right-hand side of the slide, we have some more accurate validation statistics, both for the SST with drifting buoys, moored buoys, and argo floats, and for the SST component showing almost 0 mean biases and standard deviations of 0.5. And the breakout of the IST, ice surface temperature validation with the 2-meter air temperatures, which is higher. But when we look at ice surface temperatures from the NASA ice bridge flights, and that's the last line of the table, we are actually looking at quite a different statistics. So we have biases of 1.5 degrees and a bit lower standard deviation than the others, around 3.1 degrees. And based on that multi-year product, we produce also similar ocean monitoring indicators like the ones I mentioned for the North Sea Baltic. So you see here an example of the annual mean surface temperature anomaly in the Arctic for 2023. That's the left panel. Very nice, Erica. Thank you. In the middle, we see the trends in the Arctic from 82 to 2023. So almost always positive trends above even 2 degrees in most areas. And on the bottom right side, you see the monthly mean anomaly for the Arctic, which indicates a trend of 0.1 degrees per year. And that, for the 82 to 2023 year period, that sums up to almost 4.4 degrees warming in the Arctic. So quite high compared to the North Sea, Baltic Sea domain. Yes, and with that, maybe we can move also to a teaser slide on a new product we are currently developing and will be releasing later in the year. This is a new C3S product. It's somehow seen to continue what is there available already based on the Ostia system and the Icea CCI data. We have used our own global processing chain and the version 3 Icea CCI data along with ice surface temperatures to provide a global combined sea surface temperature and ice surface temperature product at 0.05 degrees resolution, spanning the period from 1982 to 2024. The 2023 will be the climate data record, and then we are foreseeing some intermediate climate data record updates to include also 2024. This is just an example of how the product looks for a test year. This is the 1st of January 2015, so you have a global coverage and you have a combined sub-skin SST and skin ice surface temperature for the Arctic. Erica, thank you. Yeah, so in conclusion, as I mentioned in the beginning, DMI is a production unit for the Copernicus Marine Service, both for the sea surface temperature and ice surface temperature products involved in the SST tag and the sea ice tag, so North Sea, Baltic Sea, and Arctic Ocean. The products are available as daily files at near real time and also as multi-year products. They are based on a combination level 2 and level 3 SST and IST single sensor products, and quite an extensive suite of high resolution CS concentration products to define where IST should be used instead of SST. Most of our products show near zero biases and standard deviations in the order of 0.5 degrees, at least for the SST component. As I mentioned, we did the first analysis of the effective spatial resolution of the near real-time Baltic level 4 SST, and we found that is high, effectively high, and it's close to the grid spacing of 2 kilometers. And also we have a series of ocean monitoring indicators which show some alarming warming trends, both for the North Sea, Baltic Sea and the Arctic. There was some mentioning of the hourly level 4 SST product that we have not been exploring very much, and we haven't heard of any users that do so, so it would be nice to see some work. But we also have some product evolutions to do on that. So more coming up in the next, probably in the next Copernicus contract from next year onwards. And then maybe a final bonus slide, Erika, just to mention that we also have a near real-time global level 4 SST foundation at 0.05 degrees, which is not available on the Copernicus Marine Service, but it is disseminated to the PODAC and then available through the Amazon Web Services. And with that, I'd like to conclude, and I see Helen already has a question, but thanks for following.